Hi everyone, I'd like to talk about my favorite mega number. That is, my favorite number larger than a million. And it's 3 times 2 to the power of 402,653,209 minus 1. Minus 1 is very important, don't forget it. But to explain why this number is interesting, I'll need to take you down a rabbit hole. Our first stop is hereditary base notation. Now, you're probably familiar with the concept of bases and representing a number in different bases. You're watching a maths video after all. But just to recap, take 37 for example. In base 10, which is what we use on a day-to-day basis, this number is represented as 37. However, we can also write 37 in base 2, binary, and it would be 100101. We could also use base 3, which would be 1101, or base 5, which would be 122, and so on. The point is that all of these represent the same number. The way to interpret these digits is as coefficients in an expansion of powers of the bases. So 37 is 37 in base 10, because 3 times 10 to the first plus 7 times 10 to the 0 equals 37. Similarly, if we use the digits as coefficients in an expansion for the other bases, we will always get 37 because all of these represent the number 37. To understand how we get from usual base notation and get to the cooler sounding hereditary base notation, let's go back to the expansion of 37 in base 2. Let's clean up a little and remove the bits that don't matter. Next, let's turn our attention to the exponents, and we also expand them in base 2. And we keep doing this until all coefficients that appear are smaller than the bases. Now, we're almost there. Just do a final cleanup and remove once again the parts that don't matter, and this is 37 in hereditary base 2, or HB2 in short. The idea is just to expand all coefficients, exponents included, until they are all less than the bases. Now if you want to check if you got this, try working out 1080 in hereditary base 3. You should get to this result. So that's our first ingredient, hereditary bases. That, to be honest, just look like a more verbose version of the usual base system. But don't fret, because we're going to build something huge out of it. Quite literally. For that we'll need the so-called Goodstein sequences proposed by Reuben Goodstein in 1944. The sequences are built according to the following rules. We start with some number that needs to be a positive integer, and then we do steps. For step 1, we write the number in hereditary base 2. Swap all the 2's in the bases by 3's, then we subtract 1. The result is the second term of the sequence. For step 2, we take the result of the subtraction and write it in hereditary base 3. We swap all the 3's in the bases by 4's, then subtract 1. The result is the third term of the sequence. For step 3, we write the result of the subtraction in hereditary base 4, swap all the 4's by 5's, and then we subtract 1 to get the next term in the sequence. At this point I hope the pattern's clear. You just rinse and repeat, always increasing the base, and the sequence will only stop if we ever reach 0. Okay, so like with all sequences, the first question that comes to mind is, how does it look like? So let's see if we start with 1, what we get. For that we need to write 1 in hereditary base 2, which just gives us 1. We then need to swap all 2's by 3's, which still just gives us 1, and then we subtract 1, which gives us 0, which will be the next term of the sequence. Now, since the sequence reached 0, we reached the end of the sequence, and so if we start with 1, the Goodstein sequence is just 1, 0. So let's start with a larger number and see if we get something more interesting. Starting with 2, we once again write it in hereditary base 2, swap 2's by 3's and subtract 1, and get the next term of the sequence, which will be 2. We do the next step and see that the next term is 1 and then 0. So if we start with 2, the whole Goodstein sequence will be 2, 2, 1, 0. Now if we start with 3, it takes a little longer to reach 0, but not that much. The sequence is just 3, 3, 3, 2, 1, 0. Now at this point you may be thinking, this got to be the most disappointing mega number video so far. But as you may have deduced from the poorly built suspense, something big is just around the corner if we start with 4. We do the first step and right off the bat, something new happens. The sequence increases. In fact, the first terms are 4, 26, 41, 60, and it keeps growing. You can check this sequence in the online encyclopedia of integer sequences. But just like the sequences before it, this one also eventually stalls and slowly drops to 0. And the largest number it reaches is our mega number, 3 times 2 to the power of 402,653,209 minus 1. And from here on things get really wild. If we had started with 5, the sequence also eventually stops, but the largest number it reaches is on the ballpark of 10 to the power of 10 to the power of 10 to the power of 19,728. If we had started at 12, we would be way past Graham's number before the sequence finally drops back to 0. And now we finally get to the bottom of the rabbit hole and reach Wonderland, which is Goodstein's spheren. That basically says that no matter which number we use as the start of a Goodstein sequence, we always go back to 0 eventually. Now what's so special about the spheren is that all I showed you so far is pure arithmetics. More precisely what we call first order arithmetics. Now this means that Goodstein's spheren is a statement in first order arithmetics, but even though it is true, it is, however, undecidable in it. That is, it can't be proven by first-order arithmetics. To see how this works, consider all the things that are true and can be stated in first-order arithmetics. Goodstein's theorem is there. If we consider, however, what can actually be proven by first-order arithmetics, only a fraction remains and the theorem is not in it. Now, the existence of undecidable statements was nothing new. Kurt Gödel had shown they were around by the 30s. But undecidable statements tend to be either weird looking or hard to understand, and that's what I like about Goodstein's theorem. It's a relatively easy to understand undecidable statement, and the mega number I showed is one whose size gives us a hint of why this is undecidable. The idea is that the lengths of the sequences and the numbers they reach grow so fast that in a sense they break first-order arithmetics. But you may also be thinking, if that's the case, how do we know Goodstein's theorem is true? Now the answer shows an interesting quirk of undecidability. It depends on what tools we allow ourselves to use in a proof. Now Goodstein's theorem can indeed be proven in what's called second-order arithmetics, where more tools are allowed besides the ones of first-order arithmetics. The details are fairly technical, but it is obvious that doing so should increase the amount of statements we can prove. Among those that become possible is Goodstein's theorem. And this shows what I like about 3 times 2 to the power of 402,653,209 minus 1. It's part of what can be argued to be one of the weirdest parts of mathematics, which is undecidability. Its size gives us a clue about why undecidability emerges in this case. But it's also not so large that we can't even write it down precisely, as it happens to the numbers reached by Goodstein sequences that start with numbers larger than 4. Like Goodstein's theorem, it is a part of undecidability we can kinda wrap our heads around. Well, that's all, and thank you for watching.